Problem 1513, number of substrings with only one. So we're given a binary string and we want to return the number of substrings with all character ones in it. So to understand how they got the answer here, we have the substring like so. You can think of it as there being two big substrings, substring 1 and substring 2. Big substring 1 can be broken down into more substrings. We can either preserve it and do nothing, in which case it contributes a substring of length 2, or we can break it down into its constituent ones, and it contributes two substrings of length 1. And for the second one, we can either do nothing, which will preserve what we have, or we can break it down into twos, in which case there's two ways, or we can break it down into its constituent ones, in which case there's three contributions. And the way I got this here is that if I have 1, 1, 1, I can group these two together to form a substring, or I can group these two together to form a substring. So there's a total of two contributions. So if I keep a tally of all the total substrings of different lengths, well, this contributes a length of 2, this contributes 2 ones, this contributes 1 substring of length 3, this contributes 2 substrings of length 2, this contributes 3 substrings of length 1. So therefore, that's how we got the answer. There's 5 here, there is 3 here, and there's 1 here. Sum it up, we get 9 total substrings. So the observation you can make here from how we broke down each big substring is that if I have a substring of length n, I can break it down into substrings of length n minus 1, n minus 2, all the way down to 1. So let's just consider the case of substrings of length 3, right? We can break it down into its constituent ones, in which case there's 3 ways to do that. I can break it down into lengths 2, in which case there's 2 ways to do that. If I break it down into just 3, which is just the length of the original string, there's only 1 way. If I have 2, then there's 2 ways to preserve the length 2. There's 2 ways to break it down into lengths of 1, and there's only 1 way to preserve the length of 2. So what's interesting here is that it seems to form an arithmetic progression. So basically, if I know a big substring containing all ones, then the number of ways to break this down even further into substrings of length n minus 1, n minus 2, all the way down to 1 is just going to be n plus n, right, times n plus 1, n plus 1 divided by 2, which is the sum of this arithmetic sequence. And you can convince yourself that this is the case by considering a substring of length 4. Break it down case by case. If I want substrings of length 1, there's 4 ways to do that. If I want to break it down into substrings of length 2, there's 1, 2, 3. 3 ways to do that. And if I want to break it down into substrings of length 3, there's 1 and there's 2. 2 ways to do that. And if I want to preserve n, there's only 1 way to do that. So indeed, this pattern holds for any arbitrary n. So what we ultimately need to do to solve this problem from this observation is simply just, for a given substring, find all the big substrings, the big subsequences where it's just all ones. And then once we know the lengths of each of these strings inside the overall string that contains just ones, simply find the sum, right, of each term from 1 to the number. So like this is 2, so 1 plus 2 times 2 divided by 2, 1 plus 3 times 3 divided by 2. Sum this all up, and you get your answer. So that's how we're going to program it up, and we can do this in Python. Alright, so as we said, we're going to need to find the constituent ones within the overall substring here. But first, let's define the modulo. So that's going to be 10 raised to the 9th power plus 7. Now we're going to use 2 pointers. So ij is equal to 0 and 0. And what we're going to do here is while I is less than the length of s and j is less than the length of s, we're going to find the length of each constituent sequence of ones. So like we want to find this sequence and we want to find this sequence. So how are we going to do this is we're going to say while I is less than length of s and the element at I is equal to 0, then just keep incrementing I. And by the time we exit this loop, I is going to be on a 1. So set j to be equal to I. And j is the endpoint, I is the start point. And now we're going to have a count. so the count is going to be 0. And while j is less than the length of the string, and the element at j is equal to a 1, we're going to add j by 1. And when we exit this loop, j is going to be on a 0. So therefore, the count here, actually we don't even need a count. We can just find it, right? The count is simply just going to be equal to j minus I. That's the number of ones in the consecutive sequence of ones that we just found. So now we have to somehow sum it up. So res is 0, that's the accumulator, and res is going to be plus equal to some function, let's call it sum, and we pass in j minus I, which is going to find the arithmetic sum of this element, of this n, from 1 to j minus I. And after that, we set I to be equal to j, because j is added 0, so when we set I is equal to j, we have this loop to be continuously incrementing. So that's how we define the while loop, and once we're done, we just return res. So now we gotta define the sum method. The sum method takes in some number and calculates the arithmetic sum from 1 to n. So because the number could be very large, let's call t to be equal to n times n plus 1. But we want to take the modulo of this. So we take this with remainder m. And we return t divided by 2. So that is going to give us the thing. And with that, because we're continuously taking the modulo, the sum should be good. But there's a chance that res might surpass, so we can just do remainder m again here. And with that, we should have our solution, which we do. So let's submit. And there we go. That's the whole problem.